All right. Hey, everybody. Thanks for joining. So, this talk was born from a conversation between Brad and myself around some of the recent hype in the world of AI. And yeah, I have a few different takes, and he thought it was probably a good idea for me to share some of the design thinking that's gone into the way we've designed our production systems, specifically our production AI system. So, this is a talk which I'm calling From Agent Loops to Disposable Programs. And it talks about how we've been able to design our system in such a way to make our AI runtimes more reliable and affordable in production. So this is the tweet that I saw a few weeks ago that has set us out of this, the whole idea around people designing loops and meta loops in this case. And so over the weekend, I also saw some of these type of tweets, which is around loops and checklists being what you need to make agents reliable and stuff like this, where everyone's entering their loop maxing era and looping their way through to success. I have quite a few thoughts, but it's pretty interesting to see what's happening out there. And it's also more funny that while this is happening simultaneously, people are shocked and surprised that companies are trying to claw back their AI costs. And they're surprised that the AI spend is way more than they expected. So it's funny that both things are happening at the same time. And this website's pretty funny. It's called isaiprofitable.com. And yeah, as you can tell, it's there's a lot of businesses burning a lot of money in the world of AI. Now, granted, this is not AI production figures, so that is many of these costs tend to be around people using AI for building software, either that or they're using Fable to draft emails. But either way, there's a lot of money being spent in that side of things. Now, that's not really what I'm going to focus on. A lot of my focus is probably going to be more on the cost of running AI in production. But still, it is good to see that the world has started to pay attention to efficiency and cost optimization in the world of AI, which I think is a very important topic. So today's agenda for the talk is why everyone's gone loopy, how have we been told to make AI efficient and affordable, what's actually worked for me, and how we can implement this locally and how we're implementing this in production. So this is more of a general talk ahead of our Wednesday workshop. So this is meant to give a bit of a primer into how I've been thinking about these systems and prepare us for doing the deep dive onto our live system on Wednesday. Cool. A quick one about who am I, if we haven't spoken already. Hi, I'm CJ. You probably see me around the office. I'm working on the dynamic care engine, and as a bit of my background, I'm an engineer who spent the last year and a bit trying to get AI to do things a bit reliably, quickly, and cheaply at scale. And yeah, it's been quite a lot of fun. You end up trying to tackle a whole bunch of interesting problems and doing all sorts of weird things. And some of the weird things that I've been doing is prompt engineering, context engineering, harness engineering, caching, frontier models, open source models, getting AI to talk like Neanderthals because apparently that saves tokens. Yeah, lots of weird stuff in this industry and a lot of hocus pocus. But functionally, the premise of this talk is I want to posit an argument that I've had for a while now and been how I've built systems for the last year. And the argument that I make is a simple argument, which is that I think many production AI loops should just be programs. Now, this would come as no surprise to any engineer and anyone who's worked with AI systems. And to be honest, I also think that most big companies out there right now that are in the process of trying to claw back and get some cost savings, I think many of them will be coming to the same realization hopefully soon. Now, as much as I say that, I do think that loops are still important. They are fundamentally important to all agentic operations. You could argue that an agentic operation is the loop itself. And so the loops are very important for most dynamic work and discovery. So not taking that away, your back and forth chats with human input definitely is designed for loop-based input. The thing though is that loops are just expensive from a cost perspective, and that's what everyone's focused on right now with the token cost. But I also argue that loops are very expensive from a reliability and time perspective, and I don't think people talk enough about that. From a reliability point of view, look, just my opinion, but I generally think that you're lucky if your agent gets something right. You are less lucky if it deviates a little bit, but it finds its way back. You're even less lucky if it just loops indefinitely and runs out of turns. And you're just very unlucky if it responds incorrectly. And all the while, it takes time and burns tokens. And I say unlucky and lucky, not to say that people are not doing a lot of great work in their harness engineering and really increasing the probability of success, but that's exactly my point. It's the probability of success. It's not possible to guarantee success in this particular arena. And that's the thing, like loops are really hard to debug, especially in production. And as an engineer, I find this particularly irksome. And that's why I have the most empathy for anyone designing loops, because having done this for a while now, you realize that it's quite tricky. And there are just so many variables. Locally, I think it's fine when you have a human in the loop that can course correct. It's not that bad. This is why I think coding agents are awesome. I think personal agents are awesome. Things like Punklaw, Hermes, great, fantastic. I love them. They're quite good, those agent loops, because you can interact and you can course correct as you go. You can get a lot of value out of those type of systems. Now, this talk isn't about those type of systems necessarily. I don't really focus too much on that area. Most of my focus is in production. And so in the production world, you don't have as much human intervention and you're forced to rely on the harness. And so a lot of my time is spent in harness engineering. So it's funny to me that this has become a discipline in its own right. But yes, this is the world that I live in. Feedback systems, proactive guidance systems, active context mutation, dynamic discovery, all that kind of fun stuff. And at 100,000 to 1,000,000 invocations a day, trying to debug loops at a 5 to 8% failure rate, it drives me up the wall. And the thing is that there are just so many variables. It's not just the context, it's the provider config, it's the models. Some models have encrypted reasoning, so you have no idea what got in there. It's part of the input payload that got sent in, so not even your system prompt, but the input payload that was passed in from the outside. And I have a whole bunch of eval suites that I've been curating and running for a while now. And there's just so much weird behavior. Models that were passing yesterday suddenly stopped passing today on the same tests. Newer models fail some cases that older models were passing. And I think it comes down to this. We're fundamentally trying to make non-deterministic systems do deterministic work. And the whole industry is bending over backwards to try to make this thing work. And look, I have no doubt that I'm sure they'll figure it out. And I'm sure eventually we'll figure out how to do this. But it is really eye-opening when you start to realize this whole thing is being held together by twigs. I think many of you will remember this from a few years ago. This probably kicked off the whole AI can't count thing, which is the how many R's are there in Strawberry, and it got it wrong. Same thing goes with math. We talk about jagged intelligence. As smart as the AI seemed to be, the fact that they would make mistakes with calculations. Now, to be fair, this is not a surprise to anyone that knows how LLMs work, and therefore it's not really its fault because it's not designed to do this. And so that's why they introduced tools, right? Which is fantastic. So AIs can reproduce the tokens that is just seen. So we can reproduce the number of tokens, feed that into a calculator tool, and boom, let the calculator give you the right answer and do the right calculation. And so this is how they solved that problem for local execution. And then eventually people are like, oh, we'd love to talk to external systems. And so boom, comes in MCP, which is great. I think it's a good abstraction, provides discoverability, and creates a separate layer for authentication, which is required for these type of things. But the thing is that all of these tools and MCP and everything, it just feeds more into the loops and it feeds more into the context. And then the problem is that your instructions can get lost in the noise. Now, this is not as much of a problem in the world that we're in today, just because the models have gotten really good. But when I was doing this work last year, the models were nowhere near as good. And which is a testament to how far things have gone in a year's time. But the reality is, like, when I started, the models were nowhere near as good. And that's probably a good thing in a sense, because it forced me to design systems in a completely different way because I could not rely on the models. And so I had to build from that foundation. And so I had to start looking at different questions, which is, what are the models good at? And the thing that was clear to me at the time, especially with the Claude models and GPT models later, was while they can't do math, they are really good at coding up a damn calculator. And so the thing that I came to the realization of is, don't try to force the models, just meet them where they're at. And so my solution to most of the things last year was just to get the models to write code, because they were really good at writing code. And I moved most of my predictable orchestration into code. And then I just had to deal with the headache of how to run it, which is fine. Running software has been a thing I've done for over a decade, so we can figure that out. And this is not really new. This is called program synthesis, and it's been around for ages. Local models have been doing for a while. It just chains a bunch of CLI commands, or it writes out some arbitrary Python or node scripts on your machine, and it runs it because it's a more efficient way to make mass edits or do some calculations locally in your machine or run checks. So running these kind of arbitrary scripts and programs is not new. We've been doing this for ages. And the thing is, it also became quite popular to do in production. Around the same time as when I was working on doing this, there was this really good post by Cloudflare around their code mode sandboxing that they were looking at doing, which I think was a good pattern. And at the time, it felt good to know that I was not the only one that felt this way about the way things were being built in the agentic times. So it was good to see other people playing and experimenting in this space and trying to make it better. It became clear that, hey, yeah, there are better efficiencies out there, and then we can achieve these better efficiencies using programmatic methods. But there was still a problem, and even a problem with this design that they're proposing. And for me, it's that the code execution was part of the loop. And I have a fundamental problem with this design. And this is a thing that kind of held me back from it, which is I like the way that software used to be. which is like traditional software. And not traditional software in that sense. I actually just like the way that traditional software scales. So let's put this as an idea. The way that traditional software used to work is that effectively you have a whole bunch of people working on this piece of software. You pay for it up front, and not discounting maintenance, but once you finish building it, once you ship it, it scales really well. That's the beauty of software, right? As long as you've got the compute to run it, it can scale really well. And so effectively, the cost of use of that piece of software goes down over time as you reuse that software a lot more. And this is the benefit of how software could scale. And traditionally, this is how software used to work. And then now software looks more like this, where you've got AI helping out building you the software. And then tomorrow is going to look like this, where effectively there's nobody in the room. It's just the AI building all the software. And then there's a terminal computer sitting over there, but the guy is out walking his dog. And he's probably SSH'd in from a remote Claude code session or something like that. So this is what software engineering is going to look like tomorrow, right? And so the pace of building software and the cost of building software has gone down significantly. And which is why you get theses like this coming out, which is effectively stating that the cost of software is now zero. And that the main argument that custom software is now more available and easily available, which I completely agree with. I agree with the thesis. I don't agree with the title, because let's be real, software is not zero and everyone's paying the cost for software right now. However, the thing that I was always interested in is how do I achieve this traditional software scale in an AI on-demand world? Because that's actually what I was more interested in. And so it came back to the idea of what if the agents only had to figure it out once? What if we just front ran all of the expenses and didn't have to run it later? And so this is where I came to the world last year around disposable programs, which is my way of saying AI writes the programs up front on demand. You reuse the programs until you don't need them anymore. And so disposable doesn't mean sloppy. It just means that they're generated for a bounded job and they get reused while useful, and then they can get replaced when the requirements change. And so the basic argument is that you just stop paying for an AI to rediscover the same workflow every single time. You write the workflow once, or you do that discovery upfront, and then you run it as software from that point onwards. And what about runtime intelligence? A good argument is, hey, probably the reason why you had an agent in the first place was because you wanted some kind of intelligence or judgment as part of this workflow. And it makes total sense. But the truth is, this is pretty naturally flow directly into the program synthesis. There's no reason why you can't have, as part of your program, an LLM transform step, right? And this is probably how we all started anyway. So most of us didn't really start by building agents. We started building programs that had an LLM transform step or a classifier instead of an existing program. And so the benefit, though, of doing this is that now you don't need a more powerful model. You can have smaller, more focused models because they don't need to worry about the whole orchestration of the flow. They just have to worry about their specific task, which is a much better way of running in that they can be faster, cheaper, and quite reliable in achieving that specific task. And you don't need to pay the frontier model cost at that point. So as an example, let's just talk about a request triage as an example, right? So in a request triage example, in an agentic flow, effectively you have your system prompt that it has to read. It gets the ticket. It has to get the ticket unless that ticket is auto-injected into the context as part of the execution run. And then it has to loop its way through tool calls to get the right context. You have to hope that it gets the relevant context as part of the loop execution. And then it'll then go through the loop. It hopefully matches the right rules against the ticket that came through in this whole process. And then it hopefully does the right tool calls to resolve the ticket. Now, another part of this is you have to hope as well that as part of this whole flow, nothing distracts the agent from what it's designed to do. For example, prompt injection is actually a very big problem. And not just malicious prompt injection, accidental prompt injection. So something in the ticket is stating, putting some sort of a classification rule of its own or mapping of its own. And the agent, in the process of getting all this context, misunderstands which part is assistant injected and which part is part of the original source. And yeah, so we ended up doing a whole bunch of work to try to make it very clear which parts are not to be trusted, which parts are. But let's face it, it's not really in our control once it's in the context. So I think this is where it's pretty important to try to design systems in such a way that, like, this is what you end up with in the world of the agent loop. And this is where I spent a lot of my time trying to fix these type of systems and try to make them more reliable by putting gates here to make sure it can't call the wrong thing, or it's running tool calls in such a way that it enforces accuracy. But these are all the things we have to build just to make this thing work. And the world of programs just doesn't really exist. Once you build the program, effectively, yep, there's a plan, you check the plan, you get a rule map, which is a predefined rule map that it can pull. at runtime. If you have text that you want to classify, it just classifies the specific text against the rule map that was just passed in. And then it validates that, hey, yeah, this is a valid decision. And then it goes ahead and routes the ticket. It's just fixed. And then it can just do this every single time. And there's not a lot of room for the workflow to change. If anything goes into that text, it doesn't matter. It'll just get classified to one of the available rules that were allowed. And that's it. And then it will proceed. Whereas in the other system, it is possible that it could try to do something different, or the ticket itself might interfere with the operation of the agent. Now, the truth is that might be by design as well, and that is the benefit of a loop. It is very flexible, and that comes with a pro and con. But the reality here is that in an agent loop, the agent decides what it's running. You pay the reasoning cost for every run. It's harder to debug because you don't really necessarily know everything that happened in there, or it's just very hard to read the entire loop chain. But it's flexible, but it's also unstable in that regard. Whereas the workflow, it's a lot more fixed. You pay synthesis up front, and then you just reuse it. You get stack traces and logs for the execution, and it's a bit more bounded and reliable. Reliable, assuming that the program was right in the first place, which sometimes it could be wrong. Hey, double-edged sword. But yeah, the key difference at the end of the day is for a disposable program, it's just software. It's written up front, and then the models can be called only when judgment is needed. Otherwise, you can actually get away with no AI calls for things that don't need it. So even the judgment call might be optional. For example, if the default is not met or a standard grouping, then only can you call it AI. Now, it might sound like we're trying to build a plane as it flies, which is true. That is exactly what this is. But the truth is, this is what the AI world is for the most part. It's a natural fit in the sense that the current state of harness engineering also is more or less trying to build a lot of safety rails around non-deterministic behavior. So this kind of works well in the sense that at least now when stuff does go wrong, I get a stack trace, which is way better than what I was getting before. And the other thing is most production workloads tend to be predictable. So this is not your personal agents. This is not your coding agents where you're doing one-off work. Most production agents have some kind of AOP, like an agentic operating procedure, and that defines what it's meant to do. Now, naturally, these type of things are not going to be useful for chatbots because chatbots are inherently loop-based systems, and that's kind of what you want to do. You could incorporate the workflows as tool calls into a chatbot, which if you want to. But functionally, at the end of the day, if you have a procedure for processing, triaging, or doing any of that kind of stuff, those type of things could very well, instead of being an agent that's designed to run in the background, it could just be a program, right? And the whole point that I'm saying is that loops are great for discovery and programs are really good for repetition. And a quick side note as well, by the way, even in the world of like local stuff, if you want repeatability, speed, and cost effectiveness with your local agents, just get them to write you programs and scripts. And so all that I'm simply saying is if you want to take one slide away for your local development here, don't encode your workflows in prompts, as people are so focused on skills these days. Write a markdown skill and have the entire workflow designed as a skill. Personally, not the biggest fan of that. A lot of my stuff is scripts. And yeah, embed a script as part of a skill. And so that way you can just make it run the program every single time. More efficient. So if you want something for your local development, I don't know if that's how you do it, but this is how I usually do it. And again, there are so many benefits of building this because, again, number one, you get natural chaining without the loops because, again, programs. It is incredibly token efficient. Like I said, if you're reusing and you have the ability to reuse something again and again, the cost per use goes down. You have very low cost per task because, again, AI may not be there, so they may not even be an LLM call as part of the flow. And if there is, it can be a targeted LLM flow. And then you get real debuggability, which at the end of the day is a huge win for me, especially when I'm trying to build and manage these type of systems. This was a proof of concept that we were running, and they'd been running the loop-based system, and we basically turned it off and switched it over to a programmatic system, and just the cost dropped completely. And with the agent harness actually had been pretty optimized, so we had done all the prompt caching, extreme optimization, very cheap pruned context. But still, again, it's like when you're executing a program that has very minimal to no need for LLM execution, and it can run quickly, then it's no surprise that the cost just completely dropped. Because at the end of the day, you're not really competing on optimization anymore. There is no LLM call. So what are you going to do? And that's the main benefit. The other side of things that I wanted to show you is this side, which is about the time. And I thought this was very interesting. So in this case, you can see the loop system, the agent at the end of the day, sampled out of 1.2K runs that we ran as part of the POC, was the average time to completion was around 92 seconds and the standard deviation around 18.8. The minimum was 68 seconds and the maximum was 140 seconds to complete this workflow. The programmatic side again, and this is, by the way, a programmatic side that does include optional a few AI steps. was significantly faster and with a small standard deviation, more predictable and way more stable to run. And the last one is just, it's so good to have the ability to debug again. Stack traces when stuff goes wrong, when API calls break, all that kind of stuff. It's good to see it. But also just to get a holistic understanding of what the agent was trying to do when it understood the operation. So you can just see it start to finish, which is nice. But look, at the end of the day, sometimes you still need loops. Heck, you also need the loops to write the programs in the first place. So yeah, got me there. So all I'm trying to say though is that the loops are really good for where discovery is needed. One-off tasks, human in the loop exploration, great, have that. The programs are really good where it's like workflows or the success criteria is known, the API is known, and where the scale, cost, and reliability matter quite a bit. And to be honest, I've been running these type of systems even for one-off based systems, which is where Disposable comes in, and it works really well. But I have to say, a couple of necessary warnings at the end of the day. If you are doing this in production, especially, insert Uncle Ben cameo. If you are running arbitrary code, please run it responsibly, right? So especially if your platform takes input directly from customers, if you're not running these dynamically generated code in a secure runtime or a sandbox, things can go sideways really badly. And so this is where the whole harness engineering really matters, where the whole point is just don't trust what the models will do. Just completely don't trust anything the models generate. Don't trust what the models will do. It's your job to try to make sure that it's just a zero chance opportunity. And a good way of doing this type of stuff is sandboxes. It's become really easy now, especially that there's really good sandbox technology out there so that you can run a lot of arbitrary code in them. And yeah, so, I've had the chance to work on some really interesting problems and been working on them and still are working on quite a few of these, which has been quite cool. So for example, self-correcting programs, so as stuff breaks, and they will over time, the ability for it to heal itself, figure out what's wrong, and then fix itself without human intervention, pertaining back to its original directive. Long-running programs, working with clients right now to have a year-long running care plan program, effectively matching to a patient's care. And yeah, that also comes with its own set of problems, such as hot patching running programs, because things change over time, which is natural. And the second thing is just being able to track and notify hosts during actual running programs, which is quite an interesting problem to run. And then, yeah, like relatively higher volume of invocations. Now that you're running something a little bit more stable, you can run 500K, 2 million on burst invocations a day. I'm sure these are not big numbers for some organizations. It's quite fun compared to what would have cost quite a lot of money to run previously. But the other stuff that's really fun is sub 500 millisecond response times on AI stuff. Now, again, 500 milliseconds is nothing to write home about, but in the world of AI, that's a decent response time to try to track to. So these are kind of things that I've been working with a few different projects, which is quite fun. But yeah, anyway, so we have the workshop on Wednesday, which will be quite cool. So we'll have a bit of a deep dive into our own system that we're playing with right now. But yeah, in the meantime, let's see if we have any questions. Yeah, look, there are a lot of ways. So it doesn't have to be just bash. You could actually, probably one of the simplest ones that I can think of is the E2B, have Python and Node runtime. So you could just install any packages that you want in there and then execute scripts directly in Python scripts or Node scripts. So yeah, that's also possible. It doesn't have to be bash, but you can also spin up entire like proper sandboxes as well. So both are possible, depending on what you're trying to do. Yeah, that's a great question. The simple answer is the program will fail, as any software would today. If an external integration contract changes, the program is going to break. But that's what I was saying, right? This is where some of the work that I'm doing, where if the program does fail, it can do the diagnostics to figure out why and then update itself to fix what it's trying to do, and obviously notify that, hey, it's broken, something's not been running. It could be arbitrary failures, which can be retried, which is not a problem. But if it's more of a error, at that point, yes, it will probably try to fix itself. So that's some systems. Some systems you don't want to do that because you can't trust it. Yeah, it depends. Yeah. So with programs, you can have, we do have a compiler for syntax validation. Soundness is a little bit trickier to do, but for programs, you can test them. You can just test them in the sandbox before you deploy them to production. So they are versioned, they are shippable. So yeah, you can run them or dry run them before you ship them. So you can test it. All right, cool. I think we'll call it there. Thanks, everybody. And I look forward to seeing you on Wednesday.